Today we are going to discuss the digital world. I'm going to start by describing diodes. And the diode looks like the picture above is a discrete diode, but the symbol is the triangle with the straight line. Diodes come in one of two ways, either a forward bias or a reverse bias. In the forward bias, the current flows through a diode, and then in the reverse bias, the current is stopped by a diode. The diode always allows electricity to flow in one direction only and blocks the flow in the opposite direction. They may be regarded as one-way valves, and they are used in various circuits, usually as a form of protection. There are different types of diode, but their basic functions are the same. The most common type of diode is a silicon diode. It's enclosed in a glass cylinder with a dark band marking the cathode terminal. The line points towards the positive of a circuit. The opposite terminal is called the anode. The threshold point is the voltage at which diodes conduct, approximately 0.6 volts. If the current becomes too high, the diode may crack or melt. So they are used, like I said, to protect circuits. So it will protect the circuit in a radio recorder, etc. In the event that the battery or power source is connected the wrong way, the diode does not allow current to flow backwards. Therefore, it protects the electronics. So as you can see in the drawing on the upper left, I have a 9-volt going through with the diode, but if it tried to go back the other way, the current would not flow, so it would protect the electronics. So a transient protector, the drawing on the left, diagram 1, shows a relay and it shows a spike. When a relay is turned off, a high voltage can be generated for a short time. This voltage spike can damage the relay and other components. However, the diode does not allow current to pass through it in the wrong direction and short circuit the spike. There are a lot of devices, especially in our homes, that actually use relays, and our cars that use relays, and they're generally something that requires a lot of electricity to get up and running, and they have the relay. So when that relay shuts off, we want to make sure we don't damage the rest of the circuit. So the diode can also be used to protect the meter from a reverse current. So on diagram 2, we have the diode in there, and that will protect that meter from a reverse current. Transistors. Transistor allows you to control the current, not just block it in one direction. A good analogy for a transistor is a pipe with an adjustable gate. So here we see a gate in the pipe, and if the gate is blocking a lot of the water, in this example, so there's a low flow going in. If the gate is parallel to the flow, then there's low resistance and a lot of it goes through. So a diode could be considered a one-way valve, and what it's controlling is the current. So in the diagram in the lower right, you see that the current is blocked and electricity is not flowing. A transistor has 3 terminals, and you can see the symbol. I have a B terminal, a C terminal, and an E terminal. So the main path, and what they stand for is the base, the collector, and the emitter. The main path for the current is between the collector and the emitter. The base controls how much current flows, just like the gate controlled the flow of water in the pipe. So here is my bottom view of a discrete transistor. I have this link on your notes so you could actually take a look at the video, and I also included another video for you guys to watch. And interestingly, that video says that the transistor may be the most important invention for man ever. Conductivity and semiconductors. The relative ease at which electric current flows through a material is known as conductivity. Conductors like copper have a very high conductivity. Insulators, like rubber, have a very low conductivity. The conductivity of a semiconductor depends on its conditions. For example, at low temperatures and low voltages, the semiconductor acts like an insulator. When the temperature and/or the voltage is increased, the conductivity increases and the material acts more like a conductor. Metals are good conductors because a small percentage of electrons are free to separate from the atoms and move independently. Nonmetals are not as good as conductors, so they are called insulators. In an insulator, the electrons are tightly bonded to the atoms and cannot move. Since the electrons cannot move, they cannot carry current. Semiconductors, the electrons in a semiconductor are also bound to atoms, but the bonds are relatively weak. The density of free electrons is what determines the conductivity of a semiconductor. If there are many free electrons to carry current, the semiconductor acts more like a conductor. If there are few electrons, the semiconductor acts like an insulator. Silicon is the most commonly used semiconductor. Atoms of silicon have 14 electrons. 10 of the electrons are bound tightly inside the atom. 4 electrons are near the outside of the atoms and only loosely bound. So I have some history of digital and mechanical devices here. So going back to 1623, we have Wilhelm Schickard built the first mechanical adding machine, and it was lost until the 1900s, but it was actually digital. Then in the 1700s, we had a lot of special purpose analog devices that came about, and they were analog and decimal. And then in 1822 to 1842, we have Charles Babbage developed the difference engine, and he dreamed up a mechanical analytic engine, and that was digital and decimal. And I'm going to kind of jump ahead a little here as we get to more modern times. We actually have Alan Turing in 1937 developed a theory of computability and introduced the Turing machine. And it was a purely theoretical creation consisting of an infinitely long tape with binary information on it and a moving programmable read-write head that can move along with the tape. So it was digital and it was also binary. Then we have 1938 to 1941, we have Konrad Zuse built the electromechanical programmable computer. And then we start getting into the more modern age. And you'll notice a lot of these things happened during World War II. A lot of them were done in response to trying to do a lot of calculations very quickly. And then, so 1939, we have a digital computer being built. 1940, we have the first multi-terminal remotely accessible calculator. 1943, we have to 45, we have what was called ENIAC, the Electronic Numerical Integrator and Computer, that was developed by the Ballistics Research Lab. And then in 1947, the transistor was invented. And as we kind of move forward, we actually have in 1951 the first real-time computer, and then in 1974 the introduction of the personal computer. So all of these things work on digital signals or digital information. So a signal is anything that carries information. Today, the word signal usually means a voltage, current, or light wave that carries information. A microphone converts the variations in air pressure from the sound wave into variations in voltage in an analog electrical signal. So here's an example of a microphone. I'm using one right now to record this. And it is taking the wave that is my voice, the sound wave, and converting it into an analog signal. And then there is a converter inside my computer, which then takes that analog signal and makes it into a digital signal. So information can be sent and described in many different ways. Information could either be digital or analog. Digital refers to a discrete resolution of information. When I was in college, many, many years ago, we actually did have an analog computer, and I actually got to do a little programming on that. You do not see them anymore, and they are not around. So a digital signal can only be on or off. It is very different from an analog signal. So here is a digital signal, and you can see my voltage is either 3 volts or it's 0 volts. There is no in between. Similarly, if you looked at that sound wave from the microphone, there were a lot of in-betweens. And that's why there is a difference between digital music and analog music. And because a sound wave is an analog wave. So when we convert it to a digital wave, we are making an approximation of the wave, not an exact copy of the wave. So a digital watch provides the hour, the minute, and usually the second. It's not possible to determine a time up to 1/100th of a second on a digital watch that expresses time only to the second. In the traditional or analog watch, measuring small amounts of time might be difficult, but it's possible in principle to measure the time as accurately as is desired. A high-resolution digital camera can store a photo on thousands of extremely small pixels, but the image is still in discrete pieces. A traditional camera stores the photo in continually varying intensities on film. I don't know if anyone here has actually used a traditional camera in the past, but the film that you got was basically an analog thing. It was light sensitive, so different amounts of light gave our picture. And now our digital cameras are also light sensitive, and our pixels, the amount and now we're dealing with like megapixels on everything, tell me how many small pixels I'm breaking up that information into. So the more megapixels I have, the smaller each individual pixel is. So the better the picture should be, the closer it should be to what I'm actually looking at. But I don't know if anyone has done this. I recommend you do it one day just to see what I'm talking about. But if you take a picture with a digital camera or with your cell phone and you keep blowing it up and blowing it up, you'll actually start seeing that you can see the pixels. It's actually a combination of little boxes because each of these pixels is square. So when you try to zoom in more and more and more, you'll actually end up with these squares and you'll see them. So in digital phones or digital music recording, the sound is broken into discrete pieces. Analog phones and LPs, LPs are those records that we played on the old record players, can transmit and store continually varying signals. The digital signal can approach the analog signal if the pieces are made arbitrarily narrow, but it will never be completely as smooth as the analog signal. The reason, though, that digital music is so popular now is because it could be copied without any losses, and also I could store the information in much smaller things than I could analog LPs. So I can carry now in my phone or in an MP3 player a large amount of music, hours and hours of music, and even hours and hours of video, whereas in the past, I could not do that. So there also becomes a point where, yes, theoretically, the digital signal is never not going to ever be as smooth as an analog signal, but there is a limitation to people's hearing, and we can't hear the difference between a certain digital signal and the analog signal. So in this drawing, you'll see on the left-hand side the analog signal, which is continuously varying. And then the middle drawing is actually a digital signal of that same wave, but the time divisions are quite large. And then on the right-hand side, I see the digital signal with smaller time divisions, and you can see that it more closely follows the original waves. So again, an analog signal is a continuous signal over time. A digital signal is a discrete digitized signal over time. It's important that the more samples taken in the digital signal, the better it is. So increasing the number and decreasing the size of the time division in a digital signal can make the digital signal nearly as smooth as an analog signal. So what are the advantages and disadvantages of analog and digital? Digital signals are much easier to store than analog signals and are much less prone to degradation. By definition, each piece of information in a digital signal is a number easily distinguished from other numbers. A comparable analogy for an analog signal would be a graph. It is much easier to accurately copy a table than a graph. Once they have been copied several times, the table has a good chance of staying unchanged, while the graph will probably look quite different. So we talked about digital signals and the like, and now we're going to talk about electronic logic. And electronic logic is actually basically how everything works inside of our computers and chips that we use right now. So logic circuits are designed to compare inputs and produce specific output when all the input conditions are met. So logic circuits assign voltages to the two logical conditions of true and false. For example, the circuit that starts your car only works when the car is in park, the brake is on, and then the key is turned. Yes, I know a lot of new cars don't have keys anymore, they have push button starts, but there is a similar circuit that the car has to be in park, the brake has to be on, and then you push the button or the car won't start. So there is one output which starts the car if true and does not start the car if false. So here is a logic table that is made up for that situation. So if I look and the car is not in park, the brake is not on, and the key is not turned, all of those are zeros, which means that the engine will not start. I have zero voltage going through. If the car is in park, but the brake's not on, I don't turn the key, I still do have a 0 volt. If I have the car in park as 3 volt, brake is on, but the key's not turned, car still won't start. If I have the car in park, the brake is not on, and the key is turned, the car will not start. The only combination of these is if all three of those are true, then my output is true. So the car has to be in park, the brake has to be on, and the key has to be turned for this engine to start. So I will say that, as we'll see in the upcoming slides, is basically what's called an AND gate in digital logic. So all the inputs have to be true for the output to be true. So again, the only way the output to be 3 volts is when all of them are on, which only happens if all three inputs are true. So digital signals basically have two states, either a 1, which is a high or on, and a 0, which is a low or off. So the digital values are in binary format, meaning two states. So a good example is a light that is only on or off. So as you see on the bottom of the slide, I have a light that is either off or on. In binary, there are only zeros and ones. Again, these are also called base 2. So if I wanted to count in base 2, and going from 0 to 9, let's say, but I have 0 to 7 here because of the size of the slide. So in binary, 0 is 0 also. 1 is 1. But a 2 would look like a 10 in decimal because I moved that one over. A 3 would be a 1, 1. A 4 would be a 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. And then we'd have to go to another digit for 8. So voltages are used to represent logic values. A voltage present is equal to a 1. If I have 0 volts or a ground, it's called a 0. A simple switch can provide a logic high or a logic low. So here is an example of a switch. So if I have the switch up in the upward position here, it's a 1 and the current flows through. If I have it down to the ground, it's a 0. So our three primary logic gates are AND, or not. So I mentioned earlier that with the car and starting it, that was similar to an AND gate. So if I look at the AND function, if all the inputs are high, the output is high. If any of the inputs is low, the output is low. So if this input and this input are both high, the output is high. So the logic, the symbol for an AND gate is shown in this slide, little rounded little thing with this has the 2 inputs, and then it has the output. So in this case, again, for that output to be 1, both inputs have to be 1. If either of those inputs is 0, then the output will be 0. So if I look here, I have an input of 0 and 0, so my output has to be 0. So to understand the function of a digital device, we use something called a truth table. So if I look at this truth table, I have an input of 0, 0 will give me an output of 0. An input of 0, 1 will give me an output of 0. An input of 1, 0 will give me an output of 0. But if I have an input of 1, 1, then my output will be 1. It's possible to have AND gates with more than 2 inputs. The same logical rules apply. So if any input is not 1, then I'm going to have a 0. If any input is a 0, I'm going to have an input. I'm going to have a 0 as an output. So like I said with the car, that was similar to a 3-input AND gate. In an OR function, if any input is high, the output is high. If all inputs are low, the output is low. So if this input or this input is high, the output is high. So the symbol for an OR gate looks to me like a little shield is sort of what it looks like. I have my inputs, and then at the pointy end, I have my output. But the thing we have to remember with an OR gate is if any input is 1, the output is 1. If all inputs are 0, then the output is 0. So here I have 0 and 0 as my inputs. So my output for this is going to be a 0. And here is my truth table for an OR gate. And you could see that it looks very different from the AND gate, because in this case, the only combination that gives me a 0 output is if both the inputs are 0. If either input is 1, I have a 1, and if both inputs are 1, I have a 1 as an output. So the NOT function basically is what it says, right? If any input is high, the output is low. If any input is low, the output is high. So the output is the opposite state of the input. So it's also called an inverter. So here is the symbol. It looks like a little triangle with a circle at the pointy end. I have my input, I have my output. So if the input is 1, the output is 0. If the input is 0, the output is 1. So here I have my little animated slide. I have a 0 going in, which tells me I'm going to have a 1 coming out. I have a 1 going in, I'm going to have a 0 coming out. So the truth table for the NOT gate has my input of 0, my output of 1, my input of 1, my output of 0. So a combinational logic circuit is a circuit that utilizes more than one logic function, and it's called combinational logic. As an example, if a circuit has an AND gate converted to an inverter gate, this circuit has combinational logic. So if I look at this, how would you describe the outputs of this combination logic circuit? So just keep in mind, we have an AND gate, and then we have a NOT gate after it. So in my AND gate, if I have any of my inputs is 0, my output is 0. So, but once I have an output from the AND gate is 0 and it goes through the NOT gate, the output becomes 1. But if both of those are on, right, both of them are 1, then my output from the AND gate is a 0, but my out gate from this combinational circuit, because now the 1 goes into the NOT gate and becomes a 0. So the NAND gate is a combination of a NOT gate and an AND gate. So that bubble in front of the gate is an inverter. So similarly here, I have a combination of an OR gate and a NOT gate. So the NOR gate is the combination of the NOT gate with the OR gate. So the NAND and NOR gates are very popular as they can be connected in more ways than the simple AND and OR gates. So I have a truth table here to be, I would say, to kind of be assigned to you guys. But if I have a NAND gate, right, I'm actually, what I'm going to do, I'm actually going to include on your assignment for this week some truth tables and actually have you fill them out. And so we'll kind of get into that a little bit more there. But remember, if I have a 0 and a 0, if it's a regular AND gate, the output would be a 0. So then that would be a 1. And I'm sorry, this just bumped up forward. So in this case, what is the outcome of the following? So if I have a 1 going into a NOT gate, then I have a 0 coming out. If I have a 1 and a 0 in an OR gate, then I have a 1 coming out. If I have a 1 and 0 in an AND gate, I have a 0 coming out. And then I have a 1 and 1 in an AND gate, I have a 1 as my output. So digital signals can send billions of ones and zeros per second, carrying more information than analog signals. So binary code, and this table does go up to 9 digits, up to 9. So 9 is a 1001 in binary. They're also easier to store, process, and reproduce than analog signals. So this is actually something called ASCII code, and this is actually when I press the button on my keyboard, this is what goes into the computer, and the computer then says, oh, so an A is, if I press A, I am getting a 0100001 is my A. So for the number 25, I have 00100101. But for face, now remember, I'm dealing with the ASCII code. The F is 01100110. The A is 01100001. The C is 0110011. And the E is 011000101. So some of you may have studied this in math in high school, and if you go on and take a programming class or any other computer class, you probably will learn to convert from decimal to binary and also to hexadecimal, which is base 16. So in this table, I just have the decimal numbers on the left, the binary, then even base 8, and then the hexadecimal. So I will be posting some additional work in Blackboard, and I will also open up today's discussion. So if there's any questions you have about any of this information, please add some questions into the discussion board. Please look over the videos that I'm going to post, and I will be putting up a little worksheet so you guys can actually do some logic tables. So thank you, and we'll talk on the next lesson.